Swayam Prabha. Digital India. Educated India.
Okay, hello. So we are here in our second video lecture, which is on basic surveying. Now here in this, what we have done already, I would like to go through this every time in all our video lectures so that we know where we are. We have already discussed introduction to geoinformatics. When we are talking about the geoinformatics, we discussed that geoinformatics has got basically two components. Component number one is measurement of geoinformation, and component number two is management of geoinformation. Now geoinformation is everything. Whatever is there on the surface of the earth, slightly below, slightly above, is the geoinformation. So we want to measure it. In measurement of geoinformation also, there are two aspects. Number one, we want to locate where it is. That means the x, y, z coordinate of the earth features. Number two, we want to identify what the geoinformation is, whether it is a house, tree, or what. Well, whatever the information has been collected, we wanted to manage it so that we can come out with fruitful results out of the geoinformation. So that was the thing which we discussed last time. Then we looked into various tools which are used for measuring geoinformation. For example, we looked into the conventional way, primitive way, hand, rod. Then we came into the development. We talked about the land surveying, the earlier way the land surveying was used to be done. Then we talked about the electronic surveying. Well, there were some problems when we want to do the surveying because we have to occupy the ground. So what we looked into that we need to do it in such a way that we can do it fast even for those areas which are not accessible. So what we did in that case, we flew using an aeroplane, or you may remember the example of the pigeons fitted with the camera in the belly, and they would fly in the enemy terrain, take the photographs. So the photographs, which we say aerial photograph, they may be overlapping. So it is possible from these photographs that we can generate three-dimensional model of the ground, and using those models, what we can do, we can measure XYZ. You can also identify from the photographs the object, what the object is. Well, in the case of the photography, there was a problem. We have to go and fly every time. It's a costly affair. So people started thinking something more. Can there be something which is flying every time up there in this space and is observing the earth? So there came the satellite remote sensing. And we have seen how the satellite remote sensing developed from 1972 when the observation started commercially to now. There is a leapfrog jump in terms of the spatial resolution. There are data now which are available in half a meter resolution, which is very good. We saw some examples also. And using the satellite data also, we can do what we want to do in geoinformatics. That is, we can measure XYZ, we can identify what the object is. Well, one more tool which we discussed was the GPS. With the GPS, wherever you go with the receiver, you will know your position. Well, I am standing here. From here, my receiver observes the satellites, it measures the distances, computes its position in a coordinate system. So wherever I am, I will know my position using the receiver. So what we are going to do today, we are going to talk about another module, which is basic concepts of surveying. So this is our module number 2. This module will have 4 lectures, and in these 4 lectures, we'll talk about these later on, while today we'll talk about these in this first lecture of module 2, which is surveying and imaging surveying, why we need it, examples that why we need it, then some definitions. We would also like to see the difference between terms surveying and laying out, Then some basic measurements. What are the reference systems, plane and geodetic surveying. So this is all we'll try to cover in this present lecture. Before I go further, I must give you the textbooks and the reference books which I am referring, and you can also go to your libraries or you can purchase some of these books from the market. You can stop your video here so that you can note down these names properly. These are the list of the textbooks. Some more books which are the reference books. You can again stop your video here and you can note down the names of these reference books. Well, so we begin lecture number 1 of module 2 now. Well, we will try to see, because we are basically talking in this video lecture about the surveying. So we should know why surveying. To answer this, surveying as the term, the literal meaning of the surveying is data collection or information collection. We all do it in any field. So that's the dictionary meaning of surveying. As such, we, the engineers, why we are concerned with surveying? Whether it is civil engineer, mining engineer, or whether a person dealing with the geography, hydrology, environmental engineering, anything. How we are concerned with the surveying? Our concern is we would like to do the surveying basically for engineering projects as written here in the slide, or maybe for the geographical mapping. So that's our concern of the surveying. Well, I will give you one example. This example will explain that why we need surveying. Think of a house. We want to build a house. Okay, all of us, this is a very common thing. In many common sense, the answers can come. If you just think, you have to build a house. What are the steps? What do you do? Let's assume that's a big building, okay, a college building, an institute building. We want to build those big buildings. What should be the steps? Number 1, very important. There has to be a site. We need to select a site. Okay. Then number 2, we go to the area where the site has been selected and we want to know what the topography is. How is the topography? Is this a sloping surface? Is this a flat plain surface? Are there many rivers or small channels? Or is this an undulating topography? Where are the trees? Where are the existing houses? Where are the fields? What is the natural landscape? We need to know about this. So we need to know the knowledge of topography. So this knowledge of topography, I am also trying to write here in a single word, map. We need to make a map of the area, and then once we have made a map, what do we do? This is very important. Of course, you know it. You have to plan a building, a big building. Do you go to that area itself and start planning the building? No. What we do, we make a map, we take the map into our laboratory, in our office, and then we sit with the map and we start planning the things. In planning the things we take care of, well, we should not damage the existing landscape. We should not obstruct the existing channel networks. We should not destroy, the forest, which is very precious. We want to plan in such a way so that our requirements are met, as well as the natural landscape is kept as it was. So finally, what we do, working on that map, we plan our building. Well, now at this stage, you have planned the building on your map. What to do next? Think of the ground. The ground is still like that, just virgin, natural ground. Trees, fields, river networks, just like that. There is no building as such so far, but whatever you have planned on the map has to be transferred onto the ground. So this is where actually we need to transfer our building onto the site. Now throughout this exercise, where all we require the surveying. If you think about that, we required surveying in order to make a map. We wanted to measure the geo information which is present there in the terrain. Then We came to the office, we planned the building. Now we again require surveying to transfer the map or the plan which we have done in the office to the site. So this is also where we need surveying. Well, another example I would like to give you, and this is an example of town planning, and for that I have chosen the town of Chandigarh. We know it's a very beautifully planned town. But again, in this case, in order to plan a town, what we need, first of all, we need a site. So the site for the Chandigarh is, for example, as shown here in the map. Initially, when the town was being planned, what was there in this site? No town, of course. There were fields, villages, rivulets, maybe some roads. That's it. Nothing more than that. So someone went to this area. What he needs to do? He needs to know the topography. Because if I give you a task, okay, you have to plan a town, and that virgin area where the Chandigarh is established now, you have to plan a town in that, and I put you there. Can you plan the town there in the ground? No, you can't. Because while we are in the ground, we cannot see the entire area of Chandigarh in one view. So it's not possible we can plan the town there itself. What we need to do, we need to bring that area some way into our laboratory. And this is where we need to make a map. Well, the map of the area may look like, if you just forget for a while these roads here. So just forget these roads, okay. Just think of the rivers, these natural landscapes, some more rivers, the lake here. So this is what was there in the area before the town was planned. Now this map was given to a town planner. He worked over the map. He found what could be the best possible network of roads or the town planning for this area. So the town planner, he sat with the map and he planned, okay, we want to have our roads in this particular fashion. So the roads here are in the gridiron pattern, and the town was planned like that, because it was found that the town planned this way will be the most optimal planning for this particular area. So the natural landscape of the area is taken into account. Okay, where the rivers are, that has been taken into account. Where the lakes are, that has been taken into account. Okay, so and where the roads which are coming into the town, if at all they were there at the time, it has been taken into account. So this particular job we cannot do there in the ground itself. We need to bring ground into the laboratory. Well, having planned the town, again the same thing. Now the town is planned in a map, as we can see here. Here in this map, the town is planned. It's still there in the ground, there is nothing. The ground is still, same, some rivers, villages, agriculture fields, that's it. There's nothing on the ground. So what we need to do now, the next thing, we need to transfer this gridiron pattern, or we can say the town, there on the ground. So there also, this transfer the town onto the ground, we need to do the surveying. So now you know, in this exercise also, where all we require the surveying. So another example where we need surveying. Now this one more example here. This is very, very interesting example, and this is the example of Eurotunnel. As you can see here, you may be knowing also this Eurotunnel is a tunnel between United Kingdom and France. It starts from the Folkestone and goes to the Calais. Now it's very interesting civil engineering structure. Why it is so? Because this entire tunnel is underground, or we can say under sea. Up here is the English Channel, as you can see. The job was, as given in this slide, in this figure, the engineers wanted 3 tunnels, 1, 2 and 3. One is for going, coming, and is the service tunnel. You can take it like that. So we wanted these 3 tunnels, 1, 2 and 3, somewhere here inside the ground, which is deep under sea. Well, the challenge in this case, the engineers started digging from France side as well as from United Kingdom side simultaneously. They started digging from both the ends. Now the job was that while they are digging from both the ends, they should meet at one point, isn't it? It is not that they start from here and they meet and they do not meet. They just go like that. No. They should start from both the ends. They should meet at the same point with very, very accurate measurements. There should not be any deviation in these two center lines. And this, surprisingly, and of course, with the help of the technology, it happened. This is the photograph when the engineers from United Kingdom and France, they met at a single point with millimeter level accuracy. Now, how did it happen? If you start thinking about that, see, you are digging a tunnel from one end and also from the other end. You are working throughout under the ground, but still you are meeting at the same point. And your center lines are not deviating by millimeter. How did it happen? Naturally, the people who started moving from United Kingdom, they knew where they are going. And the people from France also, they knew where they are going. They were going as per some specified directions, elevations and other things. So, in doing this also, we need exactly the measurements. So, we need to measure the things. While we are planning the thing, we need to measure. When we are executing the project also, okay, I am moving in this direction. Okay, so I need to know which direction I should move. Should I keep moving straight? Should I move slightly in slope? My slope should be more or what? So these dimensions or these specifications were given by the design engineer. The job of the surveyor there was to ensure that the tunneling is proceeding in the right direction. So this is where we need surveying. There are many more examples. I will not go into the details of all of these, but there are many more examples. Deformation of a dam. A dam gets deformed with the water upstream. So we need to measure it, because if the deformations they go more than certain value, what will happen? The dam may fail. This planning, as in the case of the road, this is very interesting. There's lot of people, hue and cry now that the minarets of Taj Mahal, they are tilting. How do we say they are tilting? We need to measure it. Now, how do we measure it? So definitely we should have a way, a surveying method by which we can measure the tilt of a tower. So this is where again we can make use of surveying, because we want to measure the things. We have the techniques, we have the tools by which we can measure the geoinformation, and this is also a geoinformation, a tower, and if at all it has tilted and if it has a rate of tilt, we need to determine that. Similarly, there are some examples in military. In the case of the military, for example, the artillery bombing, they want to start from a point, they want to damage a target. So what they want to do, they want to fire the artillery in a trajectory in such a way that it will fall on the target. Similarly, same thing is applicable for the missile. In the case of the missiles, again they want to fire the missiles from a point so that it will destroy the target, and this target is a given target, a particular building. Now just think of that. The missile can be fired with certain velocity vector here. We know what kind of forces are acting on that, from atmosphere, from the gravity. So we can model its trajectory. But in order to fall at this point, in this coordinate reference, we should know the coordinate of starting point and the end point. Now the question is, how do we know the coordinates? You are firing a missile from, for example, let's say in India to other part of the world. So you should know the coordinates of the place in India as well as the other part of the world. So you need to know these two coordinates in one reference, isn't it? For example, here you know the coordinate of this point, you know the coordinate of this point in this particular reference, in this x, y and z. Once you know this, then only you know what kind of velocity vector you need to give to your missile here. so that it will exactly target this area. So there are many more examples like this where the surveying can be used. Okay, we know now that why we need to do the surveying, isn't it? We have seen so many examples. And we know what surveying is. Surveying is basically measurement of geoinformation. We want to measure the geoinformation, we want to make use of that, we want to analyze it properly so that we can come out with some fruitful results. Now the second part of that, we should know now how do we do it? What are the methods? What are the equipments which we use in doing the surveying? Well, first of all, we'll begin with definition. We'll try to define the surveying. Of course, I know now that by this time you know what the word surveying is, how it is related with the engineers, specifically civil engineer, mining engineer, environmental engineer, or maybe a geographer, a geologist. We know what surveying is for us. As far as the definition is concerned, we can define it as, is written here, art and science of obtaining quantified and qualified measurements, the interpretation of these measurements, and a meaningful presentation of result. This is what we have been talking about in all our examples so far. We want to carry out some quantified measurements. Qualified, we should be sure about the measurements. Okay? And the measurements of what? Geoinformation. We want to interpret those measurements. Analysis. We want to interpret what we have measured. And then finally, we want to present it in a meaningful way, the presentation of the result. So this definition clearly identifies or defines what the surveying is. Now what we will see, we have seen it also, but I would like to now be very specific in that. We say the surveying is of two types, or we can categorize the surveying in two categories. Number one is surveying itself. Okay, in all the projects, if you think of all the projects, what we did, in the case of the town planning, what we did, we went to the ground first, we made a map of the ground, isn't it? And then we took this map into our laboratory. So the map is here in our laboratory. So this part is called surveying. When we are bringing the ground terrain in laboratory office for working upon it, isn't it? So this is surveying, we say. Then the second part, you should be able to tell me now what the second part is. I believe you can guess it. The second part is, the map is in the laboratory, we work upon it, we plan a town on that, then this town is to be taken onto the ground. So that's the second part of surveying. And we give it a name as laying out. So what is laying out? Taking the work onto the ground as per design specifications. So what we have seen two types of surveying. Basically, these are the two things which we do in surveying. We bring the ground in the laboratory. Now we work on that. There is some plan, some building, some bridge, a road alignment. Then next job, we want to transfer it onto the ground. Laying out part. Well, having said that, what we will do, we will now look into some basic measurements. As I have written here, surveying, you have seen, is about measurements, isn't it? In both the cases, whether we are bringing the ground in the laboratory or whether we are taking a plan, a design from our map, from our laboratory onto the ground, in both the cases, we need to do measurement. Okay. Now, when we talk about the measurements, there is one thing very important. That is, whenever we do measurement, we need a reference system. This is very important. I will give you one example of that. The example is, it's about one of my friends. He comes to my house and he tells me that his son is 1 year old. Okay, my friend has a son and he is 1 year old. So I ask him, Okay, your child is 1 year old, how tall he is? So my friend tells me, well, my child is this old, this tall. I'm surprised, a bit confused. 1 year old kid and this tall? He says, yeah, he is this tall. I said, are you sure he is this tall? Your child is only 1 year old. He says, oh, I forgot. I'm sorry, I forgot to put my other hand. So he says, well, my child is this tall. So what he did, he forgot to put his other hand. Now this is very important example actually. It looks like a joke, but this is very important. Why it is important? He was saying his child is this tall. Now the moment he says he forgot to put the other hand, what he is doing? He is giving a reference now. Isn't it? So without reference, we cannot say anything about the measurement. You say a length is, let's say we say a line is there. I say it is 10. What is the meaning of 10? Nothing. It doesn't convey anything. We need a reference. What is the reference here? The reference here will be 10 centimeter. When we write 10 centimeter, what do we mean? There is a reference, a standard, for example, a little bit like this, and the length of this standard is 1 centimeter. Our this length is 10 times this length. So our this length is 10 times a centimeter. So just saying 10 doesn't convey anything. We need to convey the reference. The reference here is a centimeter, a unit centimeter. So the idea is, the point is, whenever we are doing measurements, we will need a reference. We will need a datum. Here in the case of the child, we said, well, my child is this tall. Isn't it? So what we are doing, we are putting a datum here. This point or this surface, we can say datum. Okay, so his child is this tall. Without this datum, it doesn't convey any meaning. The same thing we'll try to continue into the surveying. So what we'll do, we'll try to see the reference system for geoinformation, because our aim here is to measure the geoinformation. Okay, so for geoinformation also we need a reference. Now what could be the reference for geoinformation? What our earth is. Let us say this is the surface of our earth. Okay, as you can see here, that's the surface of earth. Okay, there are some houses, trees, rivers, okay, all those things. Now when we say we need to measure the geoinformation, or if you go back to the examples, we went to the ground, we made a map. So what is a map, by the way? If you define the map, when we make a map, what we try to do? In making a map, we try to bring the ground into the laboratory, isn't it? And you will notice what the map is. Map is a representation of the ground. Whatever is the geometry there in the ground between different objects, different features, the same geometry is brought here into the lab, and this is the map. So any measurement that we carry out on our map should be same if we measure the distance between those 2 points there on the ground. So basically our map is geometric representation, a representation in which we are preserving the geometry of the ground and then bringing it in a sheet of paper. That's the map. Well, now start thinking. In the map also, when we are trying to preserve the geometry, let us say this is an area here. In this area we have got some 2-3 features. Now this is ground. This particular area is ground. What I want to do now, I want to make a map of this area. So what I will need a system of reference. Okay, let's take it as here X and here Y. Fine. In this X and Y, I can measure the coordinates of all the points, and what I can do, I can transfer this entire thing into a little sheet, okay, where these points will be representing their positions. So for this ground, this is the map. Obviously, because the geometry which was there between these points, among these points, is preserved here. Alright. So, what we need in order to measure these, we required a reference system, x and y. Now, start thinking about the ground of our earth features. What could be the reference system when we are talking about the entire earth? Okay. I will delete all these things from this screen now. Well, what could be the reference system when we are talking of the entire earth? Can you think of some? Our earth is as such, we can take it spherical for a moment. Now like this, I want to map the relative positions of these points. What is their distance? These points may be located here, here, here. How do I measure their relative positions, their distances? Or even if I have measured their distances some way, what is the nature of the surface in between them? Isn't it? So, we need a reference. What the reference could be for our earth? The example, can we use our earth surface as such, as a reference? Let us say, I say this surface is the reference. It doesn't sound very good. How come this surface is reference? In our previous example, we had a reference like this, x and y. There you had some points, you had measured these points, okay, and your map was ready. So, the idea of the reference is you can take all these measurements with that one, and using the reference you can now determine anything. For example, I want to determine the distance from a point here to this point. What I need to do? I need to just measure this in our map, convert it to the scale, and we know what the distance is. But if you take up the ground, just think of the undulating surface of the ground. You have one point here, a third point here. Okay, we can't measure because see, ground is not a mathematical surface. Here in this case, this xy plane is a mathematical surface. It is defined mathematically. So each and every point in this surface is fixed. But as such, the natural ground is not a mathematical surface. So we cannot take the ground as such as a reference. I believe you are getting it. Then next, if it is not surface, or if the ground surface cannot be taken as a reference, what could be the reference in order to make a map of the entire earth, or maybe a part of the earth? Well, we'll see one more curve here, and this curve is called geoid. Now, what is the meaning of geoid? The meaning of geoid is, it is basically an equipotential surface. Let me define it. The meaning of equipotential surface is, everywhere in this surface the potential is same. What potential we are talking about? Well, we are talking about here the gravity. I will try to explain it here now. What is the meaning of that? See, just think of a surface here, and that's the direction of gravity, and this surface, if it is perpendicular to the direction of gravity, okay, everywhere you draw a perpendicular to the surface, and that's the direction of the gravity. So this is why we say this is an equipotential surface. Everywhere on the surface the gravity amount vector is same. Okay, so what we can do, we can define for our earth a surface like this. Can you think of a physical surface which is also a geoid? Any surface which is physically available to us and which we can say have a property of being equipotential. Well, that surface is the water body, isn't it? The surface of the water body is in such a way that everywhere the surface of the water is perpendicular to the direction of gravity. So this is a natural equipotential surface, or we can say a natural geoid. Alright? Well, now we'll talk about the geoid, how we can make use of this geoid. you must have heard of a term called MSL. Very often in all the railway stations you will find the elevation or the height of the railway station is given from mean sea level. Now what is this mean sea level? Mean sea level is also the average surface of sea, which is taken like that, or which is measured over a period of 19 years. We take 19 years so that the effect of various tides, surges can be eliminated. So this is the average surface of the sea. So the average surface of the sea will represent a geoid. Everywhere the potential is same. Everywhere it is perpendicular to the direction of gravity. Now you can visualize this surface, isn't it? All over our earth. You can see, you can have a visualization of this surface, which we say the mean sea level. So what is there? The heights of these stations, the railway stations we are talking about, is referred from the mean sea level. Now the meaning of that, if there are two stations, one here, the height of this is 127 meter from mean sea level and the height of this is 121 meter from mean sea level. What is the meaning of that? The meaning is, if this surface is mean sea level, then the height here and the height here are correspondingly these two values from that mean sea level. Okay, as we go higher in the hills, we go away from mean sea level, so the height increases. Okay, I will delete this all again and we'll come back to our same geoid thing. So I believe the geoid is clear to you. Geoid is an equipotential surface. Now how we can make use of the geoid? Well, another example I will give you here. Let us say, because we can now project each and every feature which is on the earth on the geoid. Okay, let us say we project it like this. In order to create a map, a point here X is projected on the geoid and its position here. Another point Y is projected on the geoid, here its position. Another point Z is projected on geoid. So these points are above the geoid and this point is below the geoid. Okay. Now what is the meaning of this projection? Let me give you one more example here. What is the meaning of the projection? So if you look here and down there is the floor, let us say there are some objects here. One object I keep here, another one I keep here, another one I keep here. Just visualize these three. Okay, 1, 2, 3. I want to make a map. Okay, so what is the meaning of map? I want to represent the horizontal distances between these points. So what I need to do, I need to project them in one plane. Down there is the floor. What I do, I drop a perpendicular from this point along the direction of the gravity to the floor. Similarly for this point also, along the direction of the gravity, I drop a perpendicular there on the floor for this point also. So these 3 points which are located in different XYZ coordinates in my space are now projected there in the surface. So what the map will look like? The map will look like 3 points, isn't it? So now these 3 points form my map. Now in our map we have a reference system, as we have seen, X and Y. It's a mathematical surface. Now we look into, because that was a very small example of projection, of map making, of requiring a reference. But when we look into the broad earth, we want to measure the geoinformation. We need a reference for that also. So we are talking here this utility of the geoid. Geoid is an equipotential surface and we can have a feel of the geoid. We can see it, a physical surface there as marked by the surface of the water body. Now the question is, can we use geoid as a reference for plotting or for projecting the points which are there on the surface of the earth onto it? Then the next question, because our reference has to be mathematically defined, is a geoid mathematically definable? If at all we can use the geoid as a reference, in what case we can use it as a reference? So we will try to answer those questions now. Well, as we said, the geoid is an equipotential surface, and if our earth is a perfect sphere, its geoid will be also spherical, provided the gravity, distribution of the gravity force all over the earth is uniform, or we can say the mass of the earth is uniform. So we'll have a spherical geoid like this. Not only one, we can have many geoids, because each of these surfaces will be equipotential, as in this case. So it's like onion, you can peel it off, there are many layers. So similarly the geoid, there will be many level surfaces which are possible. All are equipotential, all satisfy the condition of being the geoid. Well, as we were saying that we can project our points onto the geoid, but is the geoid mathematically definable? To look into that, if you look inside the earth, the distribution of the mass is not uniform. Somewhere it is more, somewhere it is less. Now what does it do? Because of the non-uniform distribution of mass, if I draw it again, because of this non-uniform distribution of the mass, for our earth, the geoid will be of a shape which will be different. Now this shape of the geoid is not mathematically defined. So even if we project our points onto the geoid, we do not know anything between what is happening there. In case of our simple map, each and every point is defined. You take any 2 points, you can measure the distance between these two, because this is a mathematically defined plane. But that is not so with the geoid. So basically, for making x, y measurements or the planimetry, we cannot use the geoid. Let's look into the geoid. Can we make use of geoid to measure the geoid? Okay, I will clean my slide again and we'll come back to this again. Now what is the meaning of height or elevation? Height, which is a general term, or we can say elevation. Whenever we say the height of something, we need a reference. So we are looking now into this aspect, whether a geoid can be used as a reference for elevation measurement. Well, if this surface is geoid here, there will be a geoid surface which will pass from here also, and which will be nearly parallel to this surface, as well as there will be another geoidal surface which will be passing through the point B, while this is point A. Now one thing we observe here, what is the meaning of height in surveying? In our general engineering, the meaning of height is, if you put the water droplet anywhere, that water droplet will flow as per the gravity. So the water droplet will always try to come down as per the gravity. If you put this water droplet on a surface, this is a surface, then it will flow here in this direction because of the gravity. So we say height, we say 2 points, a point A is lower than point B if the water droplet flows from B towards A. So we say point B is higher than point A. So that is the basic definition of elevation. Now how we are going to make use of geoid? The height of point B from the geoid is represented by this line. What is this? This is in the direction of the gravity. If from B we meet the geoid at this point, then this is the height of B from geoid. Let us say we write it as HB. Similarly, for point B, for point A, we can write this as HA. Well, the difference between these 2 points, if we write it as delta H A B, then that will be equal to H B minus H A. Okay. Well, we see here, how do we? This is basically what we are doing. We are trying to find this delta H A B is nothing but the difference in heights of these two level surfaces or these two joints which are passing through point A from point B. Also, because this gives us that point B as at higher elevation, because if you put a water drop here, it will tend to flow towards A. Well, if you can measure the height, but still we said the joint is not good enough to measure our x and y because it is not mathematically definable. So in that case, we have to define another surface, and this surface is called ellipsoid, which is shown here by the red color. Now, what is this ellipsoid? The ellipsoid is if our Earth's surface is slightly undulating, we can fit our Earth with an ellipsoid. Okay. So, this is the best fitting ellipsoid to the surface of the Earth for a particular part of the Earth. Maybe it is applicable more here than any other part. So, this is an ellipsoid which is fitted to the surface of the Earth. Now, this is an ellipsoid, so we know mathematically the equation of the ellipsoid. So, the same ellipsoid is shown here by the red line. Well, this ellipsoid will not be parallel to the joid because these two are different surfaces. What we can do now, we can project our points onto the ellipsoid, and similarly here. Now, what is the advantage? The advantage is I know the characteristic of the ellipsoid between these 2 points because it is mathematically defined. Once I have made a map, and in this map some points are plotted there, I know this entire surface of the map mathematically because I know it is part of a ellipsoid, isn't it? So, we need to define this reference. So, we can project our Earth points, Earth features or the geo information on the ellipsoid, and we can plot their x, y as we can see here. We can also plot the altitudes. For example, here in this diagram, the height of the point or the elevation of this point from the ellipsoid is called the ellipsoidal height. The height from the ellipsoid, ellipsoidal height. The height of the point from the joid from here up to here is the joidal height, and the difference in between joid and ellipsoid, this particular difference is the joidal separation, how the joid is separated from the ellipsoid. Well, again I will come back to one example, that why we need these references and why we need to define the references for our entire Earth. So, one example, we know if a missile is to be fired from one part of the Earth onto the other part of the Earth, both these points are on the surface of the Earth. We know, we have seen it also in the earlier, that in order to fire this missile from here to this particular point, we need to know the coordinates of this point and this point, both in one reference system. Now, what that reference system could be? Because these 2 points could be very far, intercontinental distances. So, why we need for our Earth, if that's our Earth, why we need a joid, an ellipsoid for this? A mathematically defined surface, because a point here, let us say this point A, which is here A, and this point is B, which is, for example, if A is here, let us say the B is here. The missile has to be fired from here and it has to reach its target. So we can do this thing only if we know the coordinate of point B and coordinate of point A in one reference system. And now the one reference system for us is the ellipsoid. Now how do we define the ellipsoid? The ellipsoid will be defined by a coordinate system which has its origin somewhere in the center of the earth. So we will talk about that in detail in our other lectures. So for this reason, because we need coordinates of any part of the world in one reference system, so we need to define this kind of reference system. So what this reference system is doing, it is, if you are talking the distance between A and B, it is taking the curvature of the earth also into account in order to determine the distance. And accordingly, this particular missile has been fired because we need to know about the curvature of the earth. Now there is one question, because in this case we are considering the curvature of the earth, but the big question is, do we always need to consider the curvature? Can we consider our earth to be flat, or should we always consider it as curvature? Okay, we are going to look into that. I am going to give you one little diagram here. Well, if I take a little part of the earth here, there are some features on this over the surface of the earth. What I do, I draw a tangent at any point. For example, let us say here I draw a tangent to the surface of the earth. Okay. Now when I say, let us consider the earth to be flat. If you consider the earth to be flat for measurement, what is the meaning of that? The meaning of that is, our points which are here, I am projecting those on the tangent plane. Okay. So what we are doing is the same thing what example I had shown here. We are considering our this, because this is also part of the earth, but I considered here this floor, and the floor is flat. When I projected my points onto the ground, I didn't consider the curvature of the earth, rather I simply measured the distance between the points in a horizontal plane, because I know for a small area it doesn't matter. For a small area, and this is said that up to a distance of 20 kilometer, there will be a difference in the arc and the chord. For example, for this point itself, let us say from here to this point the distance is 20 kilometer. So the difference in distances between the arc and the chord, okay, the corresponding chord, will be only 10 mm. So this distance is very less, very small. So what does it mean? The meaning is, for our small areas means, for example, let us say the engineering surveying areas, any engineering project, a dam site, a building site, okay, a town planning, a town which is spread in an area of 5 kilometer by 5 kilometer, that kind of stuff. You want to make a map for a university campus, another small area. For all those cases, we can consider our earth to be flat, because it doesn't matter. The differences in the distances is very less if you consider to be flat or no flat. Okay. So this kind of surveying, when we consider our earth to be flat, is called plane surveying.